the dark matter, and what is the origin, and also what's the connection with the Baryon asymmetry in the universe. And from the particle physics side, I will talk about the Higgs boson as the key to answer these questions. And we already know that the Higgs boson has been discovered at the Large Hadron Collider for 2 years. And it is the only fundamental scalar we have discovered in nature. And so because it is a scalar, it can be the force mediator. And therefore, I will study or talk about the possibility that the Higgs is the force that leads us to the hidden sector, to the dark sector, and to understand the dark matter. And therefore, I will discuss a few examples based on this assumption. Okay, should be here. So, okay, so let me start from the dark matter. The facts about dark matter. So we know that dark matter exists. There is very strong evidence for the existence of the dark matter in the universe. So we know from this bullet cluster or rotational curve or lensing or structure formation, and we even know how many dark matter we need to have in today's universe, which is about a quarter of the total energy. And we know several facts that's considering the properties of the dark matter. So it has to be here today, so it has to be cosmologically long-lived. And it should form structure, so it cannot be too relativistic. And also we haven't discovered the dark matter yet experimentally in the laboratory. So which means that the dark matter has to be at most weakly interacting. And another fact, which is from the theory side, is that we know we have a successful model for the standard model describing interactions of particle physics, but the standard model cannot provide a dark matter candidate satisfying all these properties. And the next thing I want to talk about is the Higgs boson. So we know the LHC has found a spin 0 particle with mass equal to 125 GeV. And then here is the CMS and Atlas result. And you can see the nice little peaks here, which is the Higgs boson. And because the Higgs boson it looks, the signal event rate looks very much like what predicted by the standard model. And therefore, we say that we have discovered the standard model Higgs boson, and that's a milestone for particle physics. And these two gentlemen have gone to Stockholm. And so here is the kind of plan of my talk. So I will discuss, as I said, because the Higgs is a scalar, can be a force or a mediator between the interactions of our sector, which all the standard model particles, and the dark sector, which we don't know what it is. It's very sketchy. And the Higgs is the bridge that's communicating between the two sectors. And therefore, the Higgs boson, in addition to giving mass to all the elementary particles, it can also do the following jobs. It mediates the interactions between the two sectors, and also because this is a very important fact is that we have discovered the Higgs boson, and we are now having this high energy colliders and also low energy experiments to probe the electroweak scale. And therefore, all these ideas of Higgs talking to the hidden sector setups can be testable, and that's a very important thing, and that's why I would like to focus on this possibility. So let me just as a warm up, let me discuss the simplest model. Everybody have thought about it. Just to have the simplest way to have a Higgs mediated dark matter, which is just to add a complex scalar singlet under the standard model gauge group, but it is stable because of some U1 or Z2 symmetry, and we can write down the Lagrangian, which is very simple. We have the standard model part, and we have this new particle. It's a scalar. It talks to the Higgs boson, and this is renormalizable cross-quartic coupling, and it also has a mass, which is the mass for the dark matter. And therefore, with this simple setup, we can already calculate what is required for this X to be the dark matter. So the most popular solution is to have the X to be the WIMP candidate, which means that when I have an X particle and an anti-X particle, because the universe is hot, these particles can talk to the standard model sector through the Higgs boson exchange and annihilate into each other. through the Higgs boson. And but after the universe expands, they are equilibrium when the temperature is high. But when the universe expands and the temperature falls, eventually this interaction through the Higgs boson is going to be too slow. They cannot find each other to annihilate. And that is the point which is called the freeze out. And where the particles, this is the thermal, this number density, and but the actual number density is going to freeze out here. It departs from the thermal equilibrium. And that's why, it becomes a constant at a later time, and we call this constant corresponds to the radical density of the day. And how much the dark matter is left depends on how strong the annihilation cross-section is. And for stronger annihilation cross-section, the leftover dark matter is fewer. And we know that the Wien-numerical states that for the weak scale cross-section, the radical density is okay. So this is the so-called Wien-numerical in the Higgs-mediated dark matter realization. But I want to emphasize that there is an important initial condition which people didn't often make explicit, which is in this case we have to assume that the particles and the antiparticles are equal in the beginning of the time. When we talk about the whole freeze-out process. And this is an assumption. It's like a boundary condition when you evolve the Boltzmann equations. But this may not be true. And let's consider another possibility that when the particle and antiparticles, they start from different numbers, and the difference I call it a delta. And then again, I can repeat the same freeze-out process. So, and when these two particles stop talking to each other, but because I start from different numbers, let's say I have more x, and then after the annihilation, the annihilation will stop when the x cannot find an x bar anti-x particle because they are annihilated away. And therefore, you can have this kind of picture where so both x and x bar depart from equilibrium, but because there are fewer x bar, so they are all going to annihilate away. And what is left over is x, and how much is left over is dictated by the initial boundary condition, which is delta. And this is the case when the annihilation cross-section is larger than the weak scale. And in this case, the final radical density does not depend on how strong the particle interact, but only depend on what is the initial condition. So this is also become a new paradigm in recent years, which is called the asymmetric dark matter. And of course, in order to realize this picture, we have to explain what is the initial asymmetry delta. Okay, but I will talk a little more about the phenomenology. So although this is a very simple model, there are more than just freeze out in the early universe. We can also have some experimental tests of this picture today. For example, if we look at this interaction, this diagram in this direction, which is a time flow, and I'm having an X particle coming in, and it interacts with a proton and neutron, which is like a target. We put a direct detection experiment, and it contains this nucleons. And then the dark matter comes in and hit the target through the Higgs boson exchange. And this is a direct detection experiment. And we are looking for dark matter in this experiment today, and therefore it will be, impels some interplay with the freeze-out picture. And also, if we look at the diagram in the from right to the left, and this is like we have the Large Hadron Collider. We start from proton-proton machine, and then we produce the Higgs boson. And then if kinematically accessible, the Higgs boson can decay to a pair of dark matter. And therefore, this gives us the invisible Higgs decay events, which we have also been looking for, and we didn't find anything yet. But in any case, the bottom line is with all these interplays, we can put the constraints in a single plot, because this is a simple model. So the horizontal axis is the dark matter mass, and the vertical axis is how strong the dark matter interacts with the Higgs. And this blue region is ruled out because the dark matter radical density will be too much. And the red region is ruled out by the direct detection, which you didn't see anything, so it gives an upper bound on the lambda. And also there is this invisible decay width, which is effective when the dark matter is below half of the Higgs mass. And it rules out everything below, for the low mass dark matter region. And therefore today they can only survive in this white region, this narrow band, and this narrow resonance region here. And the WIMP can only lie on this line, on the boundary of this line here. And the asymmetric dark matter, where you have stronger interaction, can live in this white region. So this is the current status.
How good are these calculations when lambda is so big?
Yes.
It becomes so perturbative.
Yes, if you go to very large mass, they will this
But
too.
large lambda.
Yes.
So how much can you believe these limits?
Oh, I see. So I'm doing only perturbative calculation. So, for example, if you think the perturbation is valid up to lambda equal to the square root of 4 pi, so I can go at most, I think maybe 10 or 20 PeV, and that's the most I can do. I can believe perturbation theory. And when lambda is too large, I don't know what's going to happen, but usually it's not. It becomes non-perturbative. So, and another fact I would like to emphasize is
I was mainly talking about this Lux limit because it's dependent on how much you believe in the perturbative calculation. So this right edge might move right.
Yeah. Okay. So yes. So the point I want to make is in this perturbative regime. In this regime, the direct detection is already not far from excluding all these regions in this simple model. So, for example, if the future in the next 5 to 10 years, if we wait, the Lux can, or some other experiment can improve the limit by 2 orders of magnitude in lambda, or in the cross section, 1 order of magnitude in lambda, and then you already can, squeeze this window or even rule it out because this is not very far from each other. So that is the current status of this simple model. Oh yeah, right. That's a very fine-tuned region. I don't want to talk about it. And by the way, this one, oh yeah, okay, it works. Okay. Yeah. So next, I'm going to. This is the minimum model. I would like to make sure everybody has no problem with it, right? Yeah, because this is like the warm-up, the beginning. And next, I'm going to go beyond the minimum model. And the reason I want to go beyond is because we don't really know what the dark matter is. Although minimality is a great thing, to stick to, but because we don't know what is the nature of the hidden sector, we have to be kind of open-minded and consider the dark sector being more complicated. And therefore, I'm going to, based on this minimum picture, I will discuss 2 possible extensions. One is, instead of the scalar dark matter, I'm going to talk about the fermionic dark matter. And this is the simplest extension. And I'm going to talk about, because this is a fermion, I'm going to talk about the UV completions. And in this case, I will discuss a possibility I recently discovered is the dark matter can form bound state and it changes all the predictions we had for the minimum model. And another possibility is about the asymmetry I just showed you. When there is an initial condition, I will show that the Higgs boson can not only just mediate the 2 sector interactions, it can also be responsible for generating the initial condition in the asymmetry between particle and antiparticle. And this can apply to both dark matter and baryon number, because we know the baryon number is asymmetric. And this gives us also interesting prediction, which is testable in the future, which is the CP violating Higgs scenario. Yes?
So that one, the bound state means your fermion.
Yeah. Fermion, yes.
No, that one, the bound state means you have a fermion, that one you assume.
Yeah, fermion bound state. Yeah, right. And I'll talk about it.
In the dark sector, you can have a whole building, lots of particles right there inside.
I just understand.
Maybe hadrons, like whatever, right?
That one, okay.
Right. Okay, so let's talk about fermions. Okay, so in the case of fermion, I can also do the same thing, but the only difference between fermion and scalar is that fermion, if you write down the Higgs portal and the gauge invariance, requires it to be non-renormalizable. So which means that this is a dimension 5 operator, and there is a cutoff scale 1 over lambda here. And so the point is, we can stick to this minimum model if lambda is large. So we can use the effective theory picture and repeat the same process we did before. The result will be roughly the same. But I will focus on this different possibility where the lambda is small, which means that when I talk about a process like the dark matter freeze out or scattering, I cannot just ignore what I integrated out, because I may have integrated out something that I shouldn't have. And therefore, in this case, I should discuss the UV completion. And therefore, the simplest way to UV complete the picture is to introduce another scalar singlet, which I call phi. And now it is a mediator. And the dark matter is still the chi, and it has this renormalizable Yukawa couplings to this dark matter. And also this phi has renormalizable couplings with the Higgs. And it's practically just a mixing between the scalar and the Higgs. And it's a very tiny mixing, but it mediates the interaction between the two sectors. And so this is the setup of the fermionic model. And so with this model, we can still do the same similar scattering and annihilation processes. So I will talk about when the mediator is lighter than the dark matter, the phenomenology of freeze out and scattering will be different. So first, when phi is lighter than chi do not have to annihilate to standard model directly. It can first annihilate to the phi particles, and then the phi particles can, decay later through the mixing with the Higgs boson to the standard model sector. And so there is an important thing here, is that when I want to annihilate the particles sufficiently, I have a lower bound on the G chi. And here, if I want phi not to overclose the universe to cause problems, I want it to decay before BBN. So there is a lower bound on this mixing angle, this cross. And therefore, when I combine these two vertices, I talk about the direct detection of the chi particle. I have a lower bound on G chi, I have a lower bound on the mixing, so there is a lower bound from these two facts on the direct detection cross-section. And therefore, there will be some requirement on the phi mass, because the phi determines what is the Yukawa coupling you can write here kinematically. If it is heavy enough, it can decay to muons, for example. But if it's light enough, it can only decay to electrons, and it's a much smaller Yukawa coupling. And so what we have found in our recent work is to show that the phi has, in order for this to be all consistent, the phi mass has to be above the muon threshold. So it has to be bigger than about 200 MeV. So this
why did happen?
So the thing is, if phi, let's say it's below the muon threshold, it's 100 MeV, and then it cannot decay to a pair of muons, it has to decay to electrons. Yes, but the electron, there is a Yukawa coupling here. So then the decay rate is suppressed by the electron mass, and therefore, I cannot make these three things consistent. So because there is a lower bound here, there is a lower bound here, and which means there is a lower bound here, but the direct detection has no result, which means that there is an upper bound which is not consistent with the lower bound. So that's why I have to make
just ask you afterwards.
Yeah. Yes. Okay. So this is the simple phenomenology part.
So since you are scattering, also provide.
So the next slide, the thing I'm really excited about is the dark matter bound state. So the point is that when I have introduced this additional scalar phi, in addition to mediate interactions or let the dark matter annihilate into, it can also have some back reactions on the dark matter, which is to deal with self-interactions. And this self-interacting dark matter has been a hot topic in recent days. Mainly for astrophysical interest, because it can solve some structural problem if you believe in it. And I will not talk about too much on that direction, but I will consider a more particle physics or field theory possibility, which is the bound state problem. So because this is a attractive interaction, this is a self-interaction, and the phi is a scalar, and scalar exchange is always attractive. And therefore, when I have two dark matter, for example, the simplest case, when two dark matter have phi exchange, the attractive force can let them bond. And there is a bound state condition in the two-body case, which is like this. So this means that, so the left-hand side is like the Bohr radius of this side of the bound state, and the right-hand side is like the screening length of this Yukawa potential. And so the condition is just to make sure the screening length is large enough to accommodate the bound state, the minimal bound state. So this is the bound state condition. And so let's look at the parameter space and see how many, which are the regions that allows the bound state to exist. And so these are the three plots that's for different dark matter mass. So we can look at, for example, the first one. So here, this is horizontal axis is the phi, the mediator mass, and the vertical axis is the chi mass, the cupping, the alpha chi. And so, as I said, there is a lower bound on the phi mass, which is the 2 muon threshold. So this region is not allowed. And in this blue region, there is no bound state. And in this white region, the bound state can exist. And so this is a relevant problem, and we cannot just ignore the existence of bound state because it exists in in a big parameter space. And also, this is a log scale, so which means this is really a tiny region. And so there are two types of bound state. One is the chi-chi, the other is chi-chi bar. And so the chi-chi one is not stable because even if they form a bound state, they can annihilate inside the bound state and eventually to standard amount of particles. And what is stable is the chi-chi state. And this can be formed very abundantly if there are only chi particles around. All the chi bar particles disappear. And this is, again, the asymmetric dark matter scenario. And so now we know that this bound state can exist theoretically. And now there is another question, let's put the bound state in the evolution of the whole universe and see how many of them can really be generated, because the universe is not infinitely long-lived. There is a finite amount of time. So we have done a calculation in this work. So the calculation, we only do the two-body bound state formation. So which means that the process is two free chi particle is going to meet each other and form a bound state and emit a mediator. So this is going to be the process I calculate. And so in practice, it's just the form factor is just the overlap of two wave functions. One is the Coulombic wave function, and the other is the bound state function. And so what is the best time to form this bound state? So we find that it is most efficiently formed right after the freeze out. Freeze out means that the chi and chi bar annihilate stops because all the chi bars go away. It's asymmetric. There is an initial asymmetry, and the chi can still, after this chi bar freeze out, chi can still see another chi, and that's the best time for forming this bound state because at that time the universe is still small. And therefore, this is the plot. We started. This is the formation rates in comparison with the Hubble rates we studied. And roughly you can divide it into two scenarios. One is the binding energy is less than the mediator mass. The other is the other way around. And so the horizontal axis is the temperature. This is just after the freeze out, and this is the later time. And these are the comparing the rates. So there's a big difference here. This is red line is the formation rate, and when the binding energy is less than the mediator mass, which means that when I do this interaction, the mediator is too heavy, so I cannot just form it for free. I need to employ some initial kinetic energy for this process to happen. And that's why I can only do it at a relatively high temperature, because at lower temperature, chi is too, less energetic, and so the rate gets Boltzmann suppressed. And on the other hand, when the binding energy is large enough, I don't have this suppression, and therefore the formation rate can be larger than Hubble for a very long time. And on the other hand, there is also this dissociation rate where the bound state is hit by a mediator, which is the inverse process, and forms in two free chi particles. And this is called dissociation. And this is going to stop eventually because phi decays, in the plasma, and there's no chi around it, then this process just stops. And so these are the two processes we calculate, and you can see the best way to form bound state is in this scenario, where, after this dissociation falls below Hubble, the formation rate is still there for a while. And that is the place to form bound state. And then here we again come back to this plot. So we plotted, we divided this bound state existing region in two sub-regions. So above this red line, so which is almost the region where the mediator mass is equal to the binding energy. So in this region, the bound state can form efficiently. So we are in the other scenario because in this region phi is light, so lighter than the binding energy. But in this region, it is harder to form the bound state. And you can see that, in this region, there is lower bound of this alpha, which is something like 10%, 0.1. And therefore, this is like a phase plot, so where we can form this bound state. And so we only do the calculation in the early universe after the freeze out. And so just make a point that maybe there are other, time scales that can form this bound state when the structure begins to nonlinearly grow in the later stage. But we didn't do a calculation here. Yeah. And so this is the status for the two-body bound state formation in the early universe. And now, because this is the Yukawa interaction, and the Yukawa interaction never get neutralized, which means that even I form a two-body bound state, I must still attract you to a third guy. So I can form three-body bound state and an n-body bound state. Because this scalar exchange is always attractive. And so we recently did a work, which you will see it in the next week. So the idea is to consider, the properties of this n-body bound state. Because when n is much bigger than 2, we can use some statistical mechanics picture. And so the picture implies the so-called degenerate Fermi gas picture. So we just talk about, we can talk about it in some semi-classical effective theory, where we have this Hamiltonian. So the key point is that I have this phi, which is the potential, and it is sourced by n particles. And as a back reaction, phi is going to change the effective mass of this particle because it's just the Yukawa coupling. And so these are the source and back reactions. And what we did is to minimize the energy of the system and see what we are interested in is the radius, the size of this bound state, which we call it the nugget. And so there are two interesting regions. So the first one is when the n is large but not so large. And in this region, if you minimize the energy, you find that the radius decrease with the n as a 1/3 power. And this is very similar to the degenerate star, the neutron star case, where we know that the more massive neutron stars have a smaller size. And this is because in this region, the Yukawa coupling, the attractive force is very similar to what gravity does. And therefore, there is this similar behavior. But Yukawa interaction is not gravity because, it's different theory. And when I write down this interaction, and when chi becomes relativistic, so the phi interaction is actually suppressed. When I have more and more particles, and they have more and more relativistic. And therefore, I'm going to, get more weakly interacting when the particles get more relativistic, which is the case when I make n really large. And in this case, we find that the radius is going to grow with the number n. And so here is the plot. So this is the radius, the size of the nugget, and this is the number of the particles we put in the nugget. And you can see that there is a small falling here in the beginning, in the not so large n region, and which is like the star. But later, when the particles get more and more relativistic, the interaction gets weak, so the size will grow again. And this is going to be, this is the peculiar property of the nugget we have discovered. And in the end, this n, as n goes very large, the radius will get large. And finally, the size of the nugget, the largest nugget, is cut off by the Yukawa screening. And you can see that in here, you could have something like 10,000 particles bonded together. and each of these particles has a big scale mass. So I'm going to have 10,000 big scale particle, which is like a 1,000 TeV particle. But what is good is it still have a thermal history. So which means that these chi particles freeze out as individual particles, and later the bound state form. And therefore, this is a way to get a supermassive WIMP or dark matter candidate, which still have a thermal history. And another thing is the binding energy per particle is calculated as a number of n, and you can see that it grows, pretty deep. When n is large, and depending on how large it is, it can grow, very deep.
Direct detection experiment can detect these.
I will talk about the next slide. Yeah. So, but I want to, before saying that, I want to make a remark that what I talk about is just Yukawa fermions having Yukawa interactions at the bound state, n-body bound state. So this is a very general behavior, and we are motivated by studying the dark matter problem, but maybe it has other applications like quantum matter physics, but this can be very general. And so now let's talk about the phenomenology of dark matter. So how this phenomena can change. So first, as I said, this is an example of supermassive thermal dark matter. And the second is the direct detection, where suppose I'm not having a free dark matter, I'm having an n-body bound state dark matter. And first, if all the particles are in this n-body bound state, the number density decreases just by algebra. But the rate depends on n sigma v. And if this is a bound state and everything is coherent, there will be a coherent enhancement on the dark matter side. Usually we talk about coherent in direct detection in the nucleon side when it's spin independent. But now I can have a coherent enhancement on both sides. And this is the case when the momentum transfer is small compared to the size of nugget, so that I can probe, my momentum transfer can see the whole object. But of course, there is another possibility. If the momentum transfer is large enough, I can only see part of the nugget, and I can only talk to the particles close to the Fermi sea. And in that case, I'm going to get suppression in the direct detection. So these are the two different regimes. And also, there can be very interesting indirect detection signature when I talk about nugget. And this is because of the behavior that particles are more and more deeply bounded inside the nugget. And therefore, when I have a big nugget and the capture of the free chi particle becomes n plus 1 nugget, I'm going to get the deposit in the binding energy with release through the mediator phi, and subsequently the phi decays to standard model particles. And that's going to give us, some events in the cosmic rays. I didn't do a calculation of the cosmic ray yet, but there is a hope here. And so you can also consider the accretion in stars with this Yukawa force. And the final comment is, even if we want to take the small structure problem seriously and solve it through the self-interaction in this model. And then the result may change quantitatively because people usually use the free particle self-interaction to do the analysis. But now the dark matter can form bound state, at least two-body bound state. And therefore the numbers is going to change. And the picture may even qualitatively change because of this dissipation effect. So one has to really be careful when talk about this self-interaction solving the core cosmic problem. Okay, so let me summarize the first part of my talk. So I have talked about a UV completion of the fermionic dark matter. I add a singlet phi which mediates attractive interaction. And if the dark matter number density is asymmetric, there's only chi but no anti-chi particles, I'm going to form stable bound states. So this is what I have discussed. And next, I'm going to be more ambitious. I'm going to answer the question, where is this symmetry coming from? And again, I'm going to use the Higgs boson to do the job. And so I'm going to discuss a possibility that the Higgs boson is the key to generate these initial asymmetries. And not only in dark matter, I'm also going to connect to the baryons.
I have a simple question. So the dark matter with self-interaction that can produce these nuggets, wouldn't you have dark matter halos that would show up if they had so significant self-interaction, show up in lensing?
But the thing is, this is your power copy. It screens at a very large scale. So I have a screening lens which is the inverse of 100 MeV. So that's much smaller scale compared to the size of the halo. So which means that halo scale, the dark matter interaction is still gravitational dominated.
Sure, but you could have many nuggets. I'm not saying a giant nugget, but many nuggets which would, somehow you're making your, there could be much more dark matter in a halo with this.
But there could be more bound states than free particles in the halo, but as bound states, they still have the gravitational properties of the dark matter. So
I think I think you might be thinking that do these bound states lump more because they lose energy.
Yeah,
I think the answer to these things no. Yeah. So you're saying would these become more? You're thinking they would be more essentially concentrated.
Right.
And I think you're still saying no, basically. The bound state just releases energy.
That's right. It depends on the dissipation. I didn't really do the calculation, but naively, I would think it's very hard to keep all the particles all in the very large bound state. So there will be distribution, and it depends on the distribution. It tells you how big the dissipation is.
I think the way to think about it actually is you want to have not too much dissipation, and that you have you still have to sort of preserve the observed structure of halos, right? So you kind of probably when he does the calculation in detail, you have to make sure that that's preserved. And you don't have you still see halos with the observed properties of different mass scales. So
yeah, I don't want to form a deep dark disk. Yeah.
You could
even with all the dark matter candidate.
That's not. You could put some small component of it.
That's cool.
People have constructed these types of models where some fraction of the dark matter has some small fraction has these self-interaction and dissipates into a disk, right?
From a dark disk, you really have some very efficient energy loss. For example, you have some mass zero mediator and take away all the energy. Yeah. But for them, it's not a nuclear force. It does out over some distance. Yeah. So, and also the formation of those bound states was after the dark matter phase out. So after that moment, so their self-interaction is kind of subdominant compared to expansion. Mm-hmm. Of course, that if they when they bond, they do release energy, and so in that sense, they probably have heavier elements, but I don't know how that works.
Okay, anyway, this is an open question. It deserves more careful calculation. And so next I will talk about the picture. I'll change the minimal picture. I'll talk about how the Higgs evolution in the early universe is going to source the visible sector, and it's also going to source the dark sector and to explain the genesis. This is about cogenesis. And so just to give a brief facts about the baryon symmetry in the universe. So this is what people calculate the formation of light elements during the Big Bang nucleosynthesis, and how many elements you form depends on what symmetry you put in the beginning. And you can see that all these elements favors a number for the baryon symmetry, which is like 10 to the 10 in terms of the photon number. And there is no anti-baryons today because we don't annihilate with anti ourselves. And so the question is, this is the situation today. And as a particle physicist, we would like to start in the universe with a more symmetric situation where the temperature is high, so there are both particles and antiparticles in the plasma, and they have equal amount. And so in order to reach the final condition, I have to do two stages. So the first one is the so-called Biogenesis stage, where at some stage of the early universe, some particle physics process happens, and creates more baryons than anti-baryons, which gives you this initial condition. And then afterwards, the baryons freeze out, and they freeze out through the strong interactions, which is much stronger than the WIMP. And therefore, all the symmetric parts annihilate away into photons, and only the asymmetric part, which is the red region, cannot find the anti-baryon to annihilate with. And that is the leftover today, and that is the baryon symmetry that made of the us. And so I will talk about and extend a scenario which is called the electrolyte biogenesis. which has to do with the Higgs boson, or the evolution of the Higgs field in the early universe. And this is a picture of the so-called electroweak phase transition, where as the universe cools down, the Higgs background, the Higgs has a background that prevails throughout the universe. And this is at the electroweak phase transition, the universe is transiting from the zero Higgs value to non-zero Higgs value. And the transition takes place through the bubble formation, which means that at some stage, these two vacuums are degenerating with each other, and there's a barrier. And therefore, the universe is going to transit from here to here, and the bubbles is created and it expands to infinity. And today we live in one of these bubbles. And so this is the picture, and we can make it more mathematical. So this is like the profile of the Higgs field across the bubble. And this is the outside, and this is the inside. Inside there's a valve, outside there's no valve, and the bubble is expanding. Here's the velocity. And I can make it more beautiful from my recent review. And so this is like the bubble wall. And this is the inside the bubble, the valve is non-zero, and outside the bubble, the valve is zero. And so what is the particle physics process to generate a baryon number? So the key point is that the baryon number can be broken in the standard model through this so-called spiral process, and which can translate the baryon number from zero to non-zero if there is a asymmetry in the left-handed fermion numbers. Which means that if I have some asymmetry in the left-handed fermions, then it's antifermions, and then the spiral can do the job of creating the baryon number. And the question of electroweak biogenesis is how to create this left-handed chiral charge asymmetry. And this is through the scattering of particles, CPU-relating scattering of the particles with the bubble wall, which is the particle and background interaction in a CPU-relating way. And the simplest model is to do the job is the so-called 2 Higgs doublet model. Standard model cannot do the job for many reasons, but the 2 Higgs doublet model can do. And the point is that I'm going to introduce two scalars doublets, the 2 Higgs doublet, and phi 1 and phi 2, and each of them couples to quarks in a similar manner as supersymmetry. But the difference is that I'm going to add the CPU elevation to the Higgs potential, and therefore there is a relative phase between the 2 Higgs doublet valves, Xc, which is non-zero today, and also non-zero in the early universe. And during the phase transition, this Xc is also going to evolve with time. So which means that when the valve turns on, Xc also turns on. Its time derivative is non-zero. And therefore we can do this following trick. So suppose there is this phase that gives mass to the top quark, and now the top quark mass has a phase, and I want to rotate the phase away to make the top quark mass real. But the price for doing this, if Xc has a time dependence, is to create another term from the kinetic term. And the time derivative of Xc acts like a chemical potential term, which is the source for CPU violation. It requires the left-handed particle and its antiparticle number is, non-zero. And so this is the reason for CPU violation. And then, as I said, because of the spiral effect, when this number is non-zero, the spiral can translate into the baryon number. And so this is the final baryon symmetry. And this is the picture when you use the top quark to generate a baryon number. Okay, so but next I'm going to generate. So this picture has been there for many years. It's a very beautiful picture. And what I'm going to discuss is a picture which I call Electrolyte Cogenesis, which I did recently with Zhang, is to use the Higgs field evolution, this bubble dynamics, to generate symmetries in both baryon and dark matter number. And this is based on the observation that the baryon and dark matter have similar Rayleigh densities today, and there's maybe roughly the same order. And therefore, I'm going to make the conjecture as what I assumed so far, that the dark matter number is asymmetric today. So there is a symmetry that defines how many dark matter are there. And so there are two important ingredients. And one is I have to define that new symmetry U1's global symmetry that defines the dark matter number, and which is similar to the Baryon number, U1. And there is another ingredient which is the same source of CP violation because it's cogenesis. The same CP violating Higgs sector is also going to couple to the dark matter current. And therefore, in the Biogenesis case, I have this quantity coupled to the B plus L number, and I'm also going to make a model that couple it to the dark matter number. So this is the goal, and I'll talk about these two ingredients one by one. So the first is the symmetry. So this is from left to right is the arrow of time. And this is today. So today, in order to have asymmetric dark matter and asymmetric baryons, I need two good symmetries to define them. But in the early universe, as I said, if I want to do genesis, I must break these two symmetries. And therefore, this picture, the success of this picture is based on the restoration of this symmetry at some intermediate stage. And for the baryon case, we know that in the standard model, the Higgs valve controls the spiral process, which means that when I turn on the Higgs valve, I can restore a global symmetry. And the question is what to do with the dark matter U1. And so for this handshake, I'm going to introduce a new Higgs boson, the dark Higgs boson, which I call S. And S has a charge under this U1 symmetry. And therefore, if the S has a valve in early universe, it breaks the symmetry, but if the valve turns off, the symmetry is restored. And here you can see it's amusing that you can turn on or turn off a valve to restore two global symmetries. And so this is nice, but of course, my goal is to restore the two symmetry in a single stage because it's called cogenesis. And therefore, this is the field space. So the usual electroweak phase transition happens from tunneling between the here to here, from the no valve to the Higgs valve. And but in my case, I'm going to have two directions, and I'm going to have the new dark Higgs direction and our Higgs direction. And I want the tunneling to happen from here to here, where after this happens, the Higgs turn on a valve, the singlet turns off a valve, and I restore two symmetries. And from the thermal field theory point of view, this is reasonable because these are the thermal mass of the singlet and the Higgs. And you can see that at a very high temperature, the symmetries are both restored. So we are living here. And as the temperature falls down, suppose the singlet first has a valve. So the universe goes first from here to here. And then because the Higgs has more interactions, so its thermal mass is going to change faster than the singlet. And therefore, it's reasonable to have the Higgs valve changes faster and then take over the singlet. And therefore, this becomes metastable and it's going to tunnel through a first order phase transition to the new valve. And this is my picture of new electroweak phase transition. And so this is the picture I just showed. So this is a very high temperature and no valve, and then the singlet first has a valve break both symmetries because Higgs is valveless. And then first order phase transition happens, the tunneling goes this way, and the singlet turns off a valve, Higgs turns on a valve, and it gives you the first order phase transition. And what is cute about this picture is the dark matter sector, the dark Higgs triggers the first order phase transition, but there is no net effect on the tree level Higgs couplings to fermions and gauge bosons because it's a dark matter. And the dark Higgs, it's a gauge singlet in the standard model. And the next thing is to couple the Higgs CP violation to the dark matter. And I'm going to be a bit brief here. So the key idea is to make the dark matter cease the phase, right? And the point is to use the Petrie-Quinn portal, couple it to the dark Higgs and the dark matter, X and S. So they are oppositely charged under the U1 symmetry. And therefore, their mixing, their mass term has a ceased phase. And after I do the rotation, I'm going to generate this equal but opposite symmetries in the U1, in its X and S number. And of course, I haven't break the U1 symmetry yet. And so I have to break it at some stage to get rid of this asymmetry and then define the dark matter symmetry only in X. And this can be done just by using the dark Higgs web at some point. And so here is the summary of the cogenesis picture. So this is the first order phase transition, and this is the bubble wall for the Higgs boson. And the bubble wall is CP violating, it has a time-dependent phase. And for the baryon number violation, I'm going to source the chiral charge symmetry and let it transit to baryon number in the unbroken phase. And for the dark matter sector, I'm going to take advantage of the singlet web across this bubble wall and use it to temporarily break the U1 and generate the dark matter number behind the bubble wall. So this is the new electrolyte cogenesis picture. And so for the final radical density, so the asymmetry I calculated, the baryon symmetry and the dark matter asymmetry dictated by the weak coupling and this coupling lambda. Lambda is this order term, right? And of course, I have to annihilate away the dark matter, the symmetric part of the dark matter, like the baryons. And the way is just to use the 2 Higgs doubled portal and to make sure that the coupling is large enough for the annihilation to go away. And but also I'm constrained by the direct detection. And because there are 2 couplings, I can always make some coherent destruction in the amplitude to suppress the direct detection cross-section. But of course, the more I cancel, the harder it is. And as you can see, all these red points satisfy the fast annihilation, the strong annihilation condition. But most of the points here has been ruled out by the current Xenon 100 experiment. And if we go to the Xenon 110, we improve by 2 orders of magnitude, I can kill the whole model, or if I discover this.
So is it not really point below halfway Higgs mass because you probably invisible?
Oh yeah, I didn't want it to happen. So this region I just cut it off. Yeah. So this is like the half Higgs mass. Yes. Okay. So good. So okay. So in the final few minutes, I will discuss a very exciting prediction from this cogenesis picture, which is called the CP violating Higgs scenario. So as I said, when I talk about the CP violating Higgs sector, there is a relative phase, Kc, which is related to how many baryon number is generated in the early universe. And today, this Kc is non-zero, so it's going to make the Higgs boson as a mixture between the CP even and the CP odd components. So in general, in the 2 Higgs doubled model, there are 3 physical neutral components. 2 are CP even and CP odd. This is like a supersymmetry. But when I make the Higgs sector CP violating, all the 3 components are going to mix with each other. And therefore, the mass eigenstate is not going to be the CP eigenstate. And this happens to the Higgs boson, the 125 GeV1. And it could have both CP even and CP odd couplings to fermions. And this is going to give us, physics, new CP violation signatures at the electroweak scale. And with this, tree-level coupling, I can calculate the Higgs to gluon, fusion production, and the Higgs to diphoton decay process. So these are the predictions. And so how do I? Okay, I'm going to skip this. So how do I parameterize this in 2 Higgs doubled model? So the idea is I have this effective coupling. And these couplings are all dictated by the Euler angles for the 3 scalar mixing. So there is one alpha, which is like the supersymmetric alpha. And also there are 2 CP odd angles, CP violating angles, alpha B and alpha C. And alpha B appears in the Higgs interaction with the fermions and the interaction with gauge bosons. And so this is like the CP even angle, this is the CP odd angle. This beta is like the ratio of the 2 webs. And so there are 3 parameters, and I can use this 3 parameter to fit the Higgs data because we have discovered the Higgs boson. So this is very exciting. So first I show the result the experimentalists do both the CMS and the Atlas. So they have made some constraint on the parameter space. So what they do is they assume universal coupling of the Higgs to the Z and the W boson. And they also assume the universal coupling of the Higgs to the all the fermions, only the CP even couplings, no CP odd couplings. And therefore I say there is a prejudice here. because they overlook the CP violating direction. And but you can see that this is the best point, this is the standard model point, and this is the best fit point. This is the 1 sigma region. So they claim the standard model fit very well. But actually this can be misleading, because if I open another direction in the direction perpendicular to this plane, and maybe the best fit point is here, not on that plane. And then only when I project to this plane, I see the best point is here. And actually, I'm going to show that this is going to be the case for CP violation. And there is still a sizable room for the Higgs to be a sizable CP mixture.
Yeah, you should be, look at, you just have 4 measurements, right? There are so many constraints as human in this plot, right?
Yeah, right.
These two different portions can be violated differently.
Yeah. So I have considered all these constraints, yeah.
How about the 95% CPR measurement?
Yeah, you cannot. The pure CP odd is ruled out, but between the CP odd and CP even, there is a continuous, angle, and that's the CP violation angle I'm going to talk about. Yeah. So I'll quantify how to. Okay, yeah, no problem. Yeah. Okay. Yes, so here is the plot. So you have this is horizontal axis is the alpha CP even alpha angle, and the vertical axis is the CP odd CP violating alpha B angle. And you can see that when tangent beta is around 1, this is a 1, 2, 3 sigma best fit to the data. There is a very flat direction around the tangent beta.
What is your tangent?
1.
What is the definition of your tangent?
And the ratio of V1 or V2.
What is your V1 and V2? So one is your dark matter scale, and the other is.
No, this is 2 Higgs algorithm. I'm not talking about. Yeah, this is like a superposition with just the tangent beta. Yeah. And therefore, you can see that there is this, almost a flat direction. And the reason is because it's flat because the chi-square, if you take, this alignment limit, which is constrain alpha to be almost, beta minus pi over 2, and if you focus on tangent beta around 1, the chi-square is only a function of cosine of the CP odd angle. And this cosine square is very flat around 0. That's why you can go away a lot and still be consistent with everything. And so, of course, this is the status of the Higgs data. And when I introduce new CP violation effects in the Wick scale, I'm going to worry about the electric dipole moment constraints. So I'm not going to show the details, but you can see that the dominant contribution is when you insert both CP even and CP odd couplings. And there is cancellation in this dominant contribution, which is a miracle that it happens also around the same region that's favored by the Higgs data. And therefore, this region is really a golden region to accommodate large CP violation effects. So this is what I find very exciting. And therefore, you can see it on this plot. So this is the ACME result, which is the EDM result. And these regions are all ruled out. And you can see that if you want 1 sigma, there is something like 0.2 in this CP violation angle. If you want 2 sigma, it can be even here. And therefore, there is still a very large room in having CP violation. And I also find that this result holds when there is a neutron EDM and heavy Higgs effects are taken into account. So this large room for CP violation is still there. And so when I talk about the cosmological connection, so this is the plot when I horizontal is tangent beta, and this is the CP violation. And you can see that so these are the favored region, and these are the excluded regions. So we only live in this triangular region here. These are the combined Higgs and the EDM constraints. And this is a calculation of Baryon symmetry in today's universe. And you can see that the point, this orange band is which one that fits the observation very well. And you can see that due to this cancellation and also due to the Higgs data, favored region, this is still alive. But if there is no cancellation or if there is no Higgs data improves in the future, and then there will be, this region can be in danger. So this is what this tells us. This tells us that we can review the theory. We could review the theory of Cogenesis for both baryon and dark matter by studying the Higgs physics, studying its CP violating effect at the Large Hadron Collider. And therefore the message is let's look for it harder, right? And there are several ways to discuss it, but since I'm running out of time, I'm not going to talk about it. But you can see you can do it through the Higgs decay and production, and also because there are heavy scalars, you can look for heavy scalar contributions in the CP violation. And so I'm going to conclude here. So to summarize this talk, so I have discussed the possibility that Higgs boson is the key to understand the nature of dark matter and the origin of dark matter and the baryon asymmetry. And so I will talk about two possibilities. So the first one is the UV completion of a fermionic dark matter model through the Higgs boson, and I talk about bound state properties and possible phenomenology. And another direction I talk about is the Higgs field evolution in the early universe. It can give common origins for dark matter and the baryon asymmetries. And so these are all connected to each other. And also the second one is more exciting, maybe more exciting because it is related to the CP violating Higgs physics and the EDM and collider, and all of them are going to have an improvement in the near future. So it's a very exciting field. Yeah, so that's it. Thank you very much.
Questions? Okay, so I have a small question. So if you keep this baryon to dark matter, that's the ratio. It looks like your lambda for the dark matter sector is going to be half a weak square.
Yeah.
That means it's going to be a rather weak coupling.
No, I mean, there are many couplings in this case.
So
Yeah, this is the one that for this interaction, this HEPEC portal.
Okay.
So this is the one that transfers the symmetry between the two sectors.
Because that's why you make this to share the same
Yes, exactly.
symmetry breaking
Yes,
sector.
yes. And there are other coupling lambdas. I mean, in this model, for example, you can write this absolute value square, and this couplings controls the annihilation of the dark matter, or controls more the direct detection of the dark matter. So that's separate issues. Yeah.
I mean, for the lambda one, it's small. And,
Yeah, lambda is small. Yeah.
lambda is small. Well, it's a bit lighter, and also because this is a dark sector.
Yeah, this is the portal, the dark sector, dark Higgs and our Higgs coupling. Yeah.
I was just feeling maybe the production of what's not so small.
I see. Yeah, with this small coupling, you cannot produce dark Higgs very efficiently, I guess. But the Higgs physics, it also means the Higgs physics is not effective. It's by very little amount.
Yeah, I have a question.
Yes.
So where you showed the relic density exclusion region of the parameter space and the previous one.
Okay.
The first plot you showed.
This one?
Yeah.
Okay.
So after the Higgs resonance, why is there a peak like in the?
I mean here.
Yeah.
Okay. Good question. So let me see. Okay. So there is a peak because I mean it means it excludes more, right? I mean
Yeah.
So I think it has to do with the because in this case the S can align to a pair of the W's and the on-shell W's, and when there is a new channel open, you get more constraints. Yeah. Or W or Z boson.
This may be something that's the cooling of this particle, so they become on shell at a later time. Because when it's W on shell, then all the energy above this will be the same. So the early universe, when the dark matters are moving at some higher velocities, they carry more energy. So if they couldn't miss that resonance if their masses are a little bit higher.
Yeah,
so when they
okay.
go down, they come back to that on that resonance. So that if you are going to rule out that process. But on the other side, if the mass is slightly lower, then when the universe goes down, it becomes far and far away from that resonance. So for that one, they have to eliminate on some stage. I know there's a dent, but I'm not quite sure about that deep.
Yeah.
Maybe there's a problem in symmetry.
Nice observation.
All right, so if we don't have questions, so let's thank the speaker again.